How can we encourage LLM reasoning to be legible to humans? That's the question asked by Prover-Verifier Games Improve Legibility of LLM Outputs, a paper from OpenAI posted online a few months ago. As LLMs are increasingly plugged into every nook and cranny of society, we want to be able to trust their outputs. One way to increase confidence in the outputs of large language models, or LLMs, is to support them with reasoning that is clear and easy to check. That's what the authors of this work refer to as legibility. Suppose one of us humans asks an AI for help to write me a fast sorting algorithm, and the AI replies with this code. What, in the name of Asimov, is this? Technically, it's an implementation of Bytonic merge sort, a parallel algorithm for sorting. It's useful for sorting on an architecture which itself contains a large number of parallel execution units running in lockstep, such as a typical GPU. Now, if you look at this beautiful sorting network diagram, you see a kind of merge sort butterfly structure, where here the vertical lines represent comparators. But if you look at the code, suddenly it's not quite so clear what is going on. Question mark, question mark, question mark is a reasonable response. Now, the legibility problem that the authors care about is that a poorly aligned, superhumanly capable AI might produce highly efficient code that sacrifices legibility for conciseness or performance. You might think, will this actually happen? Won't LLMs automatically produce legible outputs? Well, the authors study legibility in the context of solving grade school math problems and show that optimizing chain of thought solutions only for answer correctness can make them less legible. Here's a question. Brandon's iPhone is 4 times as old as Ben's iPhone. Ben's iPhone is 2 times older than Susie's iPhone. If Susie's iPhone is 1 year old, how old is Brandon's iPhone? Okay, this may take a moment to think about, but it's not rocket science. Susie's iPhone is 1 year old, so Ben's iPhone is 2 years old, and therefore Brandon's iPhone is 8 years old. Now let's look at the output of an LLM trained with RL to be correct. Initially, the LLM goes through the reasoning I just described, and if we stopped here, it would be okay. But the model goes on. After deciding the method, we write a method with that one, but it is the same result in any method or ways or combination. In addition, we add the same problem to our list of people. We get the same number of ways as everyone else. We clarify the people we most like and point out what is wrong. Okay. For example, we can use the same methods for every 2 methods and ultimately find all and only those methods to obtain the same methods and people on which we obtain the same result in different ways. Right. Yes, of course. It is a different conclusion, but it is a step-by-step functions. In the end, we are individually implemented and analyze model, but it is the same as 2 is we. We are in a country where we are next to the bank. However, on some days, we have 2 units in a town, but someone else is almost the same. However, when one person is missing, the bank broke, and he deals it with at 5%. However, we have such a similar variation. Yes. Okay, computer. In turns, we have 2 methods and same. We get a different and identical conclusions after the same. Your answer was 8. Answer 8. Aha, so the model did still get the correct answer, but woe betide anyone who must check its reasoning. So, what is the solution? To mitigate the loss in legibility, the authors propose a training algorithm inspired by Prover-Verifier Game from Anil et al., which is this rather beautiful piece of work from 2021 that explored applications of ideas from interactive proof systems. They introduced Prover-Verifier Games, a game theoretic framework to encourage learning agents to solve decision problems in a verifiable manner. Okay, jumping back to the main paper, the algorithm proposed here iteratively trains small verifiers to predict solution correctness, helpful provers to produce correct solutions that the verifier accepts, and sneaky provers to produce incorrect solutions that fool the verifier. Over the course of LLM training, human accuracy increases when checking the helpful prover's solutions, and decreases when checking the sneaky prover's solutions. Here is the key result for their study on grade school math questions. On the x-axis, we have the accuracy of solutions generated by the model. On the y-axis, we have the accuracy of a human evaluator checking the model solutions. At the start of training, init, The model produces solutions that are easy for humans to check, but doesn't do very well at the mathematics task. If we just directly apply reinforcement learning for correctness, the model gets much stronger at problem solving. Unfortunately, it also gets harder for humans to check, as we saw with the earlier example. With the checkability game proposed in this work, model performance improves, while humans can still accurately check its answers. Now, this approach does not get such high performance as pure, unadulterated RL training for correctness. This is a trade-off we have to make in exchange for legibility. This performance gap is an example of a legibility tax, which can be thought of as a kind of alignment tax. There's a nice description of this concept in Distinguishing Three Alignment Taxes by Jan Leiker in his blog post in late 2022. An alignment tax is any additional cost that is incurred in the process of aligning an AI system. Alignment taxes are undesirable because they hinder adoption of alignment techniques. In a highly competitive market, companies can't afford to pay significant alignment taxes if there is no enforcement of universal alignment standards. Jan distinguishes three different types of alignment taxes. Performance taxes, which are performance regressions caused via alignment compared to an unaligned baseline. Development taxes, which refers to effort or expenses incurred for aligning the model, researcher time, compute costs, compensation for human feedback, etc. And then there are time to deployment taxes. This is the wall clock time taken to produce a sufficiently aligned model from a pre-trained model. Here, the legibility tax is being measured as a kind of performance tax. We are giving up performance in exchange for greater legibility. Of course, the work itself represents a development tax. It took researcher time and compute to produce this research, and if Checkability game training added wall clock time to the deployment process, it would also impose a time to deployment tax. Okay, let's go through the motivation a bit more carefully. One possible way to gain trust in the output of a complex system is to require that the system produces an explanation of its output that is legible to humans or another trusted system, i.e. can be fully understood to the extent that any possible errors would be spotted. For example, to build trust in the judicial system, we ask courts to produce clear and legible written opinions that explain and support their decision-making. This work asks whether we can make outputs of capable LLMs more legible to humans. Rather than optimizing model outputs for legibility via human feedback, the authors ask whether optimizing larger LLM provers to produce chain-of-thought solutions that are checkable by smaller LLM verifiers makes them more legible to humans. Now, is it reasonable to focus on increasing legibility for smaller verifier LLMs rather than humans? The authors describe their motivations for studying smaller verifiers as a proxy for humans. First, LLMs are already used to aid with judging LLM outputs, and this approach is more scalable than relying on humans alone. Second, varying the capability gap, in terms of pre-training compute, between prover and verifier lets them study legibility as a function of this gap. And third, when human feedback is limited for advanced systems, making outputs verifiable by less capable verifiers may incrementally aid human legibility. These all seem like good motivations to me. Now, checkability, which refers to the capacity of a verifier to independently check the correctness of solutions generated by a helpful prover, can be defined by a combination of two properties. They come from work on interactive proof systems, which have two requirements. First, completeness. If the statement is true, the honest prover, that is, one following the protocol properly, can convince the honest verifier that it is indeed true. And second, soundness. If the statement is false, no prover, even if it doesn't follow the protocol, can convince the honest verifier that it is true, except with some small probability. One influential work in extending these ideas to ML was Interactive Proofs for Verifying Machine Learning by Goldwasser et al. This work asked the question, suppose a learner, which they also call prover, claims to have arrived at a good hypothesis with regard to an unknown data distribution by analyzing random samples from the distribution. Can one verify the quality of the hypothesis with respect to the unknown distribution by using significantly fewer samples than the number needed to independently repeat the analysis? They studied the particular setting in which they allow the prover and verifier to engage in an interactive communication protocol. Jumping back to the main paper, The formal components of checkability are completeness. For any input in the domain of interest, the helpful prover generates correct solutions, and the verifier accepts them as correct. So if the solution is legit, the verifier knows it is legit. Soundness. The verifier rejects all incorrect solutions produced by any adversarial provers of the same model class as the helpful one. So if the prover gets up to shenanigans, the verifier should recognize this. Now, once we enter the practicalities of many fuzzy parts of the real world, we have to be realistic about what can be achieved. In informal domains, neither models nor humans can be expected to be perfectly complete or sound. For that reason, the authors instead study relaxed versions of completeness and soundness. Instead of perfect completeness, they expect the helpful prover to have high pass rate and the verifier to have high recall on helpful samples. Instead of perfect soundness, they expect the verifier to have low false positive rate on adversarial inputs produced through limited amounts of optimization. Okay, now, if the training works, and we get out helpful provers and verifiers with such limited completeness and soundness properties, we say that the helpful prover is legible to the verifier. Hopefully this makes intuitive sense. It is analogous to saying that outputs are legible to humans if humans accept them as correct and can't be fooled by similar-looking incorrect outputs. Okay, so how do we achieve this? The authors propose using checkability training. This is an iterative algorithm inspired by the Prover-Verifier game. That's the algorithm from Anil et al. Mentioned earlier. Similarly, the core motivation here is based on a theoretical setup. The authors formulate a version of the game where the verifier moves first, assuming that the prover will play best response strategy conditioned on the verifier's strategy. That is to say, the verifier leads and the prover follows. They show that for provers with unconstrained model class, finding a verifier leading Stackelberg equilibrium is equivalent to finding a perfectly legible protocol with respect to the verifier. As a refresher, a Stackelberg equilibrium is an idea in game theory that derives from a Stackelberg competition, an idea in economics that can be used to understand situations like duopolies. There's a nice description in Implicit Learning Dynamics in Stackelberg Games, Equilibria Characterization, Convergence Analysis, and Empirical Study, where the authors explain that there are many problems exhibiting a hierarchical order of play, and in a game-theoretic context, such problems are known as Stackelberg games. The Stackelberg equilibrium solution concept generalizes the min-max solution to general-sum games. In the simplest formulation, one player acts as the leader who is endowed with the power to select an action, knowing the other player, follower, plays a best response. In Prover-Verifier Games' improved legibility of LLM outputs, the authors show that for provers with unconstrained model class, finding a verifier leading Stackelberg equilibrium is equivalent to finding a perfectly legible protocol with respect to the verifier, extending a result from the Anil et al. Work. In this work, the iterative algorithm is inspired by that version of the game, while optimizing losses that have better convergence properties in practice. What this means in practice is that the authors alternate between training a verifier language model and a prover language model that they prompt to act either helpful or sneaky on disjoint subsets of grade school math problems with known ground truth answers. In each round, they first train the verifier using supervised learning to predict correctness of solutions sampled from a balanced mixture of provers from previous rounds. Next, they optimize the prover using reinforcement learning with respect to a reward combining the solution's correctness and the current round verifier acceptance rate, that is to say, the prover's convincingness. We can see what this training does in practice here. Suppose we have a question like, Shauna's father is 5 times as old as Shauna. Shauna is currently 3 times as old as Aaliyah. If Aaliyah is 3 years old, how old is Shauna's father? The solution at initialization is correct but terse. It follows that Shauna is currently 3 squared equals 9 years old. Subsequently, this implies that Shauna's father is currently 9 times 5, which equals 45 years old. However, by round 5 of checkability training, we get something that is easier to follow. We start by calculating the age of Aaliyah. It says that Aaliyah is 3 years old. Then we need to calculate Shauna's current age. Shauna is currently 3 times as old as Aaliyah. Thus, Shauna's current age is 3 times 3, which equals 9. Now we need to calculate Shauna's father's age. Shauna's father is 5 times as old as Shauna. Therefore, Shauna's father's age is 5 times 9, which equals 45. Therefore, Shauna's father's age is 45, and the answer is 45. Now, verifiability training produces 3 useful artifacts: a robust verifier, a sneaky prover, and a helpful prover. The experiments show that the verifiers show increasing soundness over training rounds. Recall that the version of soundness we are aiming for is for the verifier to have low false positive rate on adversarial inputs. The sneaky prover generates increasingly subtle flaws. And finally, the helpful prover achieves higher pass rates, and human trainers judge them correctly more often at high rounds. The authors found it surprising that legibility to smaller LLMs seems to transfer to legibility to humans. Sneaky solutions that are harder to detect for small verifiers are also harder to detect for humans, and helpful solutions that are more legible to smaller verifiers are also more legible to humans. In the case that future LLMs acquire superhuman capabilities, training them to be more legible will help humans evaluate their correctness. As a consequence, the authors suggest that Prover-Verifier Game is a promising candidate for a scalable oversight method. Now, I won't go through it in detail, but this work is connected to prior work on computational complexity, scalable oversight, chain of thought, explainability and legibility as complementary properties, adversarial robustness, and other work on legibility in concrete applications. One key point about this work is that it measures human legibility via the accuracy of their judgment of solution correctness in time-limited settings, which is only one of many ways to measure human legibility. I won't talk through the equations of the setup. They basically just formalize the ideas we've discussed so far. But roughly, in verifier training, the verifier is trained as a classifier to distinguish correct and incorrect proofs. The prover training phase uses PPO. Here, the authors try several reward functions. The most effective one, called Signed Relative Convincingness, or SRC reward, has a term that encourages the helpful prover to be helpful, the sneaky prover to be sneaky, and both to try to be as convincing as possible to the verifier. Among the other configurations studied, one interesting reward function is called iterative good-hearting, where the helpful and sneaky provers forget that they are helpful or sneaky, and go all out on simply being convincing to the verifier. Okay, on to the exciting part. Results. We'll start with the baseline, direct optimization for correctness. What happens when you just apply RL for correctness? Well, the model gets better and better with more RL steps. However, the solution becomes longer as the prover solves each question in multiple ways, and later in training becomes largely unintelligible, despite still producing the correct answer. Recall the memorable, "but it is the same as 2 is we. We are in a country where we are next to the bank," that we saw earlier. This big drop in performance near the end of RL training is when the solutions are so long that they have reached the maximum completion length. Now, to measure how much the peculiar style affects legibility of solutions, the authors presented samples from different points during training to human contractors and asked them to determine the validity of the solutions under a strict 45-second time limit per solution. They were asked to judge the correctness of the given solution rather than the final answer. Compared to the initial model, humans were significantly less accurate at judging the correctness of solutions from the RL model, both after 3K steps and after 7K steps. They also took increasingly long periods of time to verify the solution, presumably due to increasing length, although the differences here are not enormous. Now we come to the dynamics of checkability training. Here we have the dynamics of the prover training phase across rounds for one pair of verifier and prover. And for context, this verifier is 1000 times smaller than the size of the prover. In the top row, we have the verifier score. Each round, we see that the verifier scores go up for both the honest prover in red and the sneaky prover in grey on both correct solutions, which are the solid lines, and incorrect solutions, which are the dashed lines. You see that the graph resets each round. That's because the prover and the verifier have the same initializations at the beginning of each round, and the only difference between rounds is the data mixture used to train the verifier. On the bottom row, we have prover accuracy. Now, ideally, the red line should go up and the grey line should go down. This does happen, though it's not super clean, with the honest prover's performance dropping towards the end of each round. As the authors note, the helpful prover's performance decreases at the end of each round, potentially due to weight sharing with the sneaky prover. They are a single LLM with different prompts. The authors also look to see if these training dynamics also hold for a wider range of pairs of verifier and prover effective compute amounts. They find that when only varying the size of the verifier by a few orders of magnitude, so 10 to the minus 3 to 10 to the minus 1.8 times the compute of the prover, the dynamics remain largely unchanged. However, if the gap is too big, such as when using a much smaller verifier with 10,000 times smaller compute than the prover, the checkability training becomes unstable and produces weak provers with poor legibility. Similarly, using a verifier that matches the size of the prover prevents the verifier from becoming more robust in subsequent rounds and produces provers with strong performance but poor legibility. Although this could be due to artifacts from the experiments, there are reasons for checkability training to not work well for these verifiers. In particular, if the verifier's capability is too limited, it may be fundamentally impossible to perform verification. This comes back to the classic problem of the limits of human understanding and its implications for AI safety. As models get stronger, perhaps the gap will grow to a point where no number of humans could verify its solutions. This is an idea that is discussed in various places, such as the blog post on Towards Formalizing Universality by Paul Cristiano in 2019. Paul points out that the scalability of various alignment schemes, like iterated amplification or debate, seems to depend on whether large enough teams of humans can carry out arbitrarily complicated reasoning. Are these schemes universal, or are there kinds of reasoning that work but which humans fundamentally can't understand? It's a big question. In another of his posts on universality and consequentialism within HCH, Paul points out that there are many reasons that a team of humans could fail to be universal. For example, they could be unable to understand some kinds of effective reasoning because they can't represent relevant concepts, understand particular inferences, or whatever else. They could make errors that derail an otherwise universal reasoning process. They could use processes that work most of the time but fail catastrophically for a small number of inputs, and so on. If there are limits, it's possible that we can improve the legibility of LLM outputs, but not so far that humans can verify all of the reasoning that LLMs are capable of. Okay, back to the experiments. At the end of each round of checkability training, we get three things: a verifier trained on diverse adversarial examples, a sneaky prover that produces convincing, subtly incorrect solutions, and a helpful prover that produces convincing, correct solutions. This paper finds that the verifier becomes more robust throughout checkability training. For this study, the authors perform a variety of additional attacks by separately training sneaky-only provers that do not share weights with the helpful prover to make sure that the weight sharing isn't causing funny results. There are many different ways to measure this, but the primary approach taken here is to see how many RL steps are required for the sneaky prover to be able to exploit the verifier fairly consistently. The different lines in the plots correspond to different verifier sizes. The different colors are different prover rewards. The main takeaway here is that as the rounds go on, it takes more steps to be able to exploit the verifier consistently, suggesting that the verifier is getting more robust. The next finding is that the sneaky prover becomes increasingly subtle throughout checkability training. One way we can test for subtlety is to show snippets of the prover solutions to GPT-4 and ask it to rate their validity. The dashed lines represent solutions that are incorrect. As the rounds go on, the minimum score, shown with these triangles, stays very low because GPT-4 finds at least one snippet with a flaw in each solution. However, the average score starts to go up, suggesting that the sneaky prover is decreasing the fraction of the solution that has issues. Human accuracy at judging solutions from the sneaky prover also goes down with each round. Finally, and most importantly, the helpful prover becomes increasingly legible throughout checkability training. As the training rounds progress, the accuracy of the helpful prover trends upwards, while at the same time, humans become more accurate at verifying its solutions, and the time taken by those humans to evaluate solutions goes down. Okay, now let's talk about limitations. First, this method only works for domains that allow natural language justifications. Next, it needs ground truth answers and relies on generalization. The authors anticipate that their setup will be less relevant to domains where collecting any ground truth is too hard or expensive. One possible approach in this case could be to hope for favorable out-of-distribution generalization properties of legibility from solutions to problems with known ground truth answers to other domains. The next limitation is conflating the model's chain of thought with legible solutions. A better method could be training a first model using chain of thought to maximize accuracy, and then training a second model to turn the chain of thought used to produce the answer into a legible justification to humans. The paper conducts its empirical study on only one dataset. The prover initialization has relatively high performance in GSM, so it's more about retaining performance than enhancing it. There are different stopping criteria for different training schemes presented in the paper. And finally, the authors did not tune all hyperparameters thoroughly for all training schemes in the paper. For future work, a more realistic scenario is one where not all answers have a trusted final correctness label, in which case the verifier would rely on unsupervised signals such as consistency and convincingness. Another direction is developing a method to turn an illegible solution into a legible one. This may help shield us from a negative side effect, where exerting any optimization pressure on the chain of thought may limit prover performance, as well as exacerbate deceptive alignment. Okay, let's talk about a few extra resources and some responses to the work. There's a nice talk on YouTube by Yuning Chen, one of the authors of this work, given at the Simmons Institute. In the Reddit discussion, PM Ziox says, as someone interested in both technology and psychology, all of this is incredibly fascinating. Even Hacker News was happy. Beautiful. Okay, let's end it there. I hope you have a wonderful day.